Welcome to the start of our algorithms videos. So we're going to be going through a few algorithms, and we're going to start with this first algorithm for graph traversal. And specifically, this one's going to be our breadth first graph traversal, and our next one will be depth first. So, if you had a list or something and you wanted to iterate through the whole list, and, maybe you're counting something, maybe you're analyzing something, who knows what you're doing, but you want to iterate through the whole list, that's a very simple thing to do, right? You could just make a for loop. You could just, go down the list, or you could say while, or, whatever. Pretty simple. But if you're looking to iterate all throughout a graph, and specifically in a way where the edges matter, it's much less straightforward because graphs don't have a first and last node. Specifically, graphs are maybe not connected as well. And you also might not even know the full graph when you're starting your traversal. And sometimes that's a point of traversing, right? Is to get to know the graph. You might have individual data points, but you might not have the whole graph. So this is used in finding shortest path algorithms. This is used in web crawlers, and we're going to show a couple other times of where it can be used as well. But the idea is, how can you go through an entire graph and explore it, find things about it, and then do something with it? And that doing something is going to be a little arbitrary for now, and that's what this video addresses. So we're going to start by talking about the breadth first algorithm. I always say breadth instead of breadth. But anyway, breadth. The BFT, the breadth first traversal. Okay. So we can just abbreviate that BFT and then make my job a lot easier. Breadth first traversal. And before talking about that, we're going to introduce a data structure called a queue. So what is a queue? A queue is, of course, just a line, and it's a line of nodes waiting to be used. So basically, just like any other line that you may, hopefully any other line, there's no cutting or anything like that. This is also known as first in, first out. So you may have seen that before. First in, first out. I don't really like writing it like that, but that's another definition that we have right here. And basically, right, you have, let's say that we have some waiting nodes here. Some nodes that are waiting in line, like good nodes. Then, of course, what the queue is that if, they're waiting in line, then if you want to get in line, you got to join at the end. And this is called enqueuing a node. Wait, hold on. Did I spell that right? I'm just going to write to enqueue a node. I don't actually know how to spell enqueuing. There's too many vowels in that word, man. Okay, to enqueue a node, right? You just get in at the end of the line, and then, once it's your turn, you get to go. And that's called dequeuing. And that's basically what we're going to be doing in this breadth first traversal, in this BFT. We'll just put some nodes in line, and then we always just take the node whose turn it is. The first person to get in line is going to be the first person to get out of line. That's what that FIFO means. Okay, I don't actually know if anyone says it like that. First in, first out. Anyway, here we go. So let's introduce the algorithm. We're going to specifically introduce the algorithm with an example here. Instead of just going and writing down a ton of things and then not really making sense of it, let's do it with an example. So we'll introduce our algorithm, our BFT algorithm, which of course is just a set of steps that you can follow, just a list of instructions, just like when you're programming or something, that are going to get you to the end result. And we're going to do it with this graph. So this is a graph. We can think about this as, a very simplified social media mutual follows. It does have to be mutual follows here because notice this is an undirected graph. It's not a directed graph. And maybe we're curious about in this school or in this class, who follows who. And we might also be curious, right? Is this class connected? Is there a path from any student down the list of follows to any other student? And of course here, when we see the graph, we can answer all those questions very quickly. No, it's not connected. Yes, we know who's following who's friends with who, whatever. When you see the graph, it's obvious. But of course, right, in reality, we're not going to be seeing these graphs. These graphs are going to be humongous. Okay, if you think of actual social media networks, if you think of actual like internet, like web pages for the search algorithms, web crawlers, massive, we can't see it. So we have to work our way through it. But of course, I'm not going to do a massive graph in an example, but that's the idea. Just keep in mind, right, that this algorithm seems silly when we can just see the graph, but the whole point of the algorithm is so we can blow it up on a massive scale. And then yes, computational time is a thing. We'll touch on that very briefly, but not very much here. Okay, so our first step is going to be choose a starting node. All right, and it doesn't matter in our case which one you start. When we talk about shortest path algorithms, then of course we'll start with the node that we want to be our start for our path. But just in general, if you're trying to traverse the entire graph, it doesn't matter which one you start with, as long as the graph is connected. If it's not connected, it will matter, right? If it's not connected, whether we start with Danielle or start with Adrian will definitely matter, because one will be a very short algorithm. Okay, so here we've chosen Greg. We're going to start with Greg. So we did it. All right, we're starting with Greg. The second step is going to be to mark that node, and then we're going to enqueue it. Now, I haven't mentioned what marking is, but marking just basically says, hey, we don't want to look at the same node twice. Let's keep a record of what we've done. All right, so I'm going to mark a node. You can do that however you want. Maybe I'll just, give it a little X. Is there anyone named Mark here? No, that's a missed opportunity. All right, so I marked a node. We've now looked at Greg, made a note. Let's have our queue on the bottom. Greg is in the queue. We are ready to look at Greg. That's step 2. Now, step 3 is the actual interesting step, right? These are just, step 1 and 2 are just initialization, right? It's just getting us started. But step 3 is our actual loop. So we have an actual while loop right here. While the queue is not empty, you're going to do the following. So of course, we can run the while loop because the queue is not empty. Greg is in the queue. There's not very much in the queue, but it's not empty. So we're going to dequeue. I feel like I'm saying disqualified. We're going to dequeue the front node. So Greg has been waiting in line, not very long, but we're going to dequeue him. So we take him out of the queue. Queue is empty for now, but we'll see what happens. All right, so we've taken him out of the queue. That's great. We're looking at Greg, but we've taken him out of the queue. We're going to visit the node. And when I say visit the node, it's like do whatever we need to do with the node. So now if we're just counting people, if we're just trying to see if it's connected, we're not doing very much. But like in the shortest path algorithm, there's going to be a set of steps that we're going to do at each node, looking at the current shortest path, comparing it to like other options of shortest paths. So depending on what your goal is, why you're traversing the graph, this do it step, the visit the node step, could be much more involved. Okay, so this is just whatever you're trying to do with that, with this graph, with this node. So in this case, we're not really doing very much. So we're just going to go through and see all the nodes. And then step C is going to be mark and enqueue all unmarked adjacent nodes. Order doesn't matter. All right, so let's go through that. We're going to mark and enqueue all unmarked adjacent nodes. So what are the adjacent nodes? Remember, adjacent nodes are different from connected nodes. Connected nodes were if there's a path between them. Adjacent is if there's an edge between them. So there's only 2 adjacent nodes here, Chuck and Izzy. We've marked them, and now we're going to enqueue them. So now we have Chuck and Izzy. The order doesn't matter which way we put them in. All right, we marked them, and we enqueued them. And all right, that's it for step C. What's next? That's it. That's the whole algorithm. So of course, we just start our while, like we just keep going in our while queue. Or our while loop, sorry. I was reading this, our while loop. So let's go back to A. Let's dequeue the front node. All right, Chuck, you are up. We are looking at Chuck now. We have dequeued him. He has gone. All right, and then step B, we visit the node. Okay, whatever information we need to record about Chuck, we're doing that now. And then we mark and enqueue all unmarked adjacent nodes. So there's only one adjacent node that's unmarked. So we're only doing it with Adrian. So we mark him and put him in at the back of the line. This would be easier if I weren't doing on a whiteboard because my line is moving. I want Izzy to go to the front of the line, but it's just going over to the side. And that's fine for now. It'll become less fine later. Okay, and then we just keep going. All right, so now Izzy's up. So we're going to take her out of the queue. And now we're going to visit the node, record, and do whatever we need to. And then mark and put in the queue everyone adjacent to her that's not already been marked. So we have Elaine over here. All right, hold on, let's see if this works. Hey. All right, great. Good. And then I kind of lost where I was at. I think we finished all that step. We added Elaine, and then we go through. It's Adrian's turn. Take Adrian off of the queue, visit the node, mark everything that's connected that's unmarked, put them in the queue. Jackie's here, so you can really see what's happening. I'll do a couple more steps, all right? I think it would be a good idea if you also pause the video and did the rest of this on your own. I think that would be really good practice. It's going to be more interesting very soon. We got more stuff coming up. So I think that'd be a good exercise. So pause the video and do that out. All right, so it's Elaine's turn. Take her out of the queue. Do whatever we need to do to mark Elaine. And then what's connected? Faith and Kim. So add both of those in any order. All right, just like so. We're good to go. Then we'll do Jackie. Remove Jackie from the queue. Mark everything that's connected and unmarked, which is only Brittany, right? Elaine's already been marked. So we put Brittany in here. And of course, we are going to have some interesting things happen now because everything is marked. So we're just going to finish this by saying, all right, let's remove Faith from the queue. Do whatever recording information we need with Faith. And then there's nothing to add. There are no unmarked adjacent nodes for Faith. Then do the same thing with Kim. Then do the same thing with Brittany. And now we have traversed the graph as much as we could. Okay, so that is one way of getting through all the nodes in this graph in that order that we just went. And we've marked them all. And again, we're never going to get to Danielle or Hank. They are not connected with the rest of the group. And that's the idea for what breadth first looks like. That's the BFT. And again, the doing step, the visiting step is often the useful step, right? In the meantime, we're just going through all the nodes in an order, but this is really where the work gets done. But for purposes of this discussion, for showing off the BFT, that's exactly how you do it. So that's pretty much it. And we got a DFT in the next video, depth first. What do you think that's going to be? Yeah, you probably know. To summarize though, real quick, right, it really was breadth first, because if you look at the steps in which we did it, right, we did Greg first, and we did Chuck and Izzy after that. Then we did Adrian and Elaine after that, right? And so you can see, right, that we are just spreading out as much as we can. And of course, depth first is just going to kind of be diving in one direction until that doesn't work, and then we'll go in another direction. And of course, breadth first, right? We're just slowly eking out from home, taking a couple steps one direction, going back home, taking a couple steps the next direction, going back home. The deepest path algorithm in comparison, right, will just be going down the whole path until we get to a dead end, and then going back until like to the last fork in the road, and then keep on going until there's a dead end and that stuff. Okay. Anyway, we'll talk more about the DFT in the next video. Not DFT, not the DFT, just DFT. But anyway, have a good one. Bye-bye.